Okay, so for this video, I'm going to be talking about topics 1 through 4. This first question looks at topics 1 and 2. Part A uses buoyancy and Part B uses hydrostatics. Our assumptions are that water is incompressible with constant density, the process is steady state, the pebble is fully submerged in the water, and that since the sink is open to the atmosphere, the pressure of the air gap in the pipe is 1 atmosphere. If the water is at 2 meters and then there's a pebble in there. Okay, for the solution, we can find, or we're asked to find, the buoyant force acting on the pebble and then the volume of the water displaced. So we have to use buoyancy equations, and the first one we're going to use is Archimedes' law, saying that the weight of the object is equal to the weight of the displaced fluid. And the weight is also equal to mass times gravity, which is also equal to density times volume. And so we have the object on the left and the displaced fluid on the right, and we can solve for the volume of the displaced fluid with all of these values that we have. And then buoyancy also says that the buoyant force is the same as the weight of the object. And so we can say that this force is also equal to the weight of the displaced fluid. And so since we just found the volume of water, we can plug all of these values in and we get the buoyant force acting on that object. For part B, we can use hydrostatics because we have a stagnant fluid, which is another assumption that this fluid is not moving because it has to be static to use hydrostatics. And then we know pressure at point 1 is 1 atmosphere because it's open to ambient air. And so we have all of these values. This is properties for the fluid, and we just plug them all in and we get the pressure at the bottom. Okay, for question 2, we are looking at topics 3 and 4. We have to assume that there's no friction in the sink head, but there is friction in the pipe. There's also no work. The process is steady state. Water is an incompressible Newtonian fluid with constant density and viscosity, and the pipe is circular with laminar flow, which is necessary for when we do the friction factor. Okay, for this first part, we have to use the Bernoulli equation, and we're going to look from points 2 to 3 to find the pressure at point 2. And so this is the Bernoulli equation right here. And not really anything can be counted out because with the assumptions that we have, none of these terms are equal to 0 right now. But we can find the velocities based on the volumetric flow rate that was given to us. And so we can just plug in all of these values, do some rearranging, and we get the pressure at point 2. But then trying to find the pressure at point 1 is a little bit more difficult because we have to account for friction. So this is the extended Bernoulli equation, accounting for the friction factor and the work. But work is 0. We do have friction. The velocities at point 1 and 2 are the same, and so they cancel out. And they're the same because the area is not changing and neither is the density. And so those are going to equal each other. Z1 is 0 because that is our lowest point. And so we can do some rearranging to solve for P1. But then we also need some way to quantify this F value. And so we have an equation for this F value so long as the fluid is a Newtonian fluid, the pipe is circular, and that the laminar, or the flow is laminar, which we all have. So we can use this equation here and we know everything in it. And so all we have to do is plug and chug, making sure our units are the same, and we get the pressure at point 1. And then we're doing a y-directed momentum balance. So this is topic 4. We have to do it in the y direction because the fluid is flowing down this way if this is positive y down that way. Okay. And so for our momentum balance, we have to account for our convective forces, which are here, and then our external forces, and then d mu dt. So this is 0 because it's steady state. The forces we have acting on it are the pressure and the bolts, and then our convective in and out. So the pressure at point 2 is this internal pressure, but point 3 is ambient pressure because this comes out through the head. And so we can do some rearranging and solve for F bolts, and we get this value.